Welcome back everyone. Today we will learn how to simulate multi-component rigorous distillation column in DWSIM software, which is free open source chemical process simulator. In the end of this video, you will able to utilize shortcut distillation method to simulate the rigorous distillation column, and you will learn how to specify the column pressure profiles, and finally how you can analyze column profiles such as temperature profile, flow rate profile, and component fraction profile inside the column, and finally the desired product specification. So to understand, to learn these concepts, we are going to solve a problem in DWSIM, and the problem statement is there is a feed consisting of alkanes like propane, isobutane, isopentane, normal hexane and normal heptane at the following mole fraction which is given in this table. So the feed is a saturated liquid which enters into the distillation column at a 2 bar pressure and 500 kilomole per hour flow rate. And in this feed we are specifying isopentane as a light key component and normal hexane as a heavy key component. So the reflux ratio inside the column is 1.5 times of the minimum reflux ratio, and the distillate coming out from the distillation column is at 1.8 bar, and in distillate the heavy key component, that is the normal hexane, should not be more than 1 mole percent. On the other hand, in bottoms the light key component, that is the isopentane, should not be more than 1 mole fraction. So in order to simulate distillation column in a rigorous way, we must have to answer these questions, that is what would be the minimum reflux ratio, what would be the actual number of stages, what is the optimum feed stage location. So in order to separate the mixture of these hydrocarbons, so in order to answer all these questions, first we will solve this problem using shortcut distillation method, and then after having the answer of these questions we will further move to specify a multi-component rigorous distillation column to have our final results. So let's move to the DWSIM software to solve this shortcut distillation problem to move further. Okay, so when you open DWSIM software, it should like the first appearance of the software would be like this. To start a new simulation, go to the file menu and then simply click on new process simulation model. So now this new wizard window will open, and in this wizard the first thing is you have to specify all the components which would be involved in the simulation. Okay, so the first component is propane. Just write propane and click here, so it is automatically be added into the simulation. The next one, butane. Write butane and select isobutane, and then similarly add the other components, that is pentane, and select isopentane, similarly hexane, and select normal hexane, and the last one is heptane. So N heptane. So all the components which are given in our problem statement has been selected, that is propane, isobutane, isopentane, normal hexane, and normal heptane. So yes, all these are selected. The next step is like Aspen High-Sys and Aspen Plus. We have to select the thermodynamic property package. So for this we will use Ping Robinson. Okay, and then go to the next. From here you can choose the unit set, which would you like. Here I will choose C5, that is default, because all of my units that I want are already specified here. And after that, just press this finish button. Okay, now we are ready to create the simulation. The first thing is just select this material stream and drop it into the canvas. Similarly, this one is the feed stream, this one is distillate stream, this one is bottom product stream. Similarly, we have to add two energy stream. One is for condenser duty, another one is for reboiler duty. Okay, after uh, introducing the feed streams, now it's time to add a column. From this ribbon, just click on columns and select shortcut distillation column and drag it into the distillation environment. Okay, so now we can, if we want, we can change the name of feed streams, energy streams, but I will take I will remain as the default, because the MS stream, material stream 1, material stream 2, material stream 3, but even we can change it. For example, material stream 1 is feed, just write feed and press enter. Similarly, material stream 2 is a top product. I am just writing top. Material stream 3 is a bottom product. Similarly, energy stream 1 is a condenser duty, so I am just writing condense D. And energy stream 2 is a reboiler duty, so reboiler T. Okay, and this one is the shortcut distillation column. So after that, just right click on shortcut distillation column and now connect the stream from left side of this ribbon. It says connections, and in feed stream just connect feed. In distillate stream connect top. In bottom streams connect bottom. In condenser duty connect con D, and in reboiler duty reboiler D. Okay, so now the next step is you have to specify which one is the light key component in your simulation. So we are having isopentane as a light key component and N-hexane as a heavy key component, and we want that the light key component mole fraction in bottom should be 0.01. That is that is asked in the question, you can see here. And similarly, the heavy key component should be 0.01 in distillate, so it is already specified. Reflux ratio is 1.5, so it is just the initial guess, we are not going to change it. And condenser pressure, in problem statement it is asked that the condenser or the distillate pressure should be 1.8 and the bottom pressure should be 2, so we are going to change it. It would be 1.8, and the reboiler is 2 bar. Okay, so now we specify the shortcut distillation column specification. It's time to specify the feed stream. Just click on feed, and from left side of this feed stream property window, go to the input data. From there, go to the stream conditions, and the flash spec is temperature and pressure, but in problem it's said that the feed is at 2 bar pressure and saturated liquid, so we have to choose pressure and vapor fraction. Okay, and the feed pressure is 2 bar, and feed flow rate is 5000 kg mole per hour, and the because feed is a saturated liquid, so vapor fraction should be 0. And after specifying the feed condition, now it's time to specify the component molar fractions. By default, DWSIM equalize the amount of each component, like here propane, isobutane, everyone has a 0.2 mole fraction. So from the problem statement, we are going to change according to our need. That is, propane is 0.05 and then 0.1. Okay, I am going to change 0.05, then 0.1, then 0.3, and 0.45 and 0.09. I think this one is 0.46. Yes, 0.46. Okay, now the sum of all mole fraction is equal to 1. Just press accept changes. Now the feed stream is completely specified according to our condition. It's time to run a simulation. For that, just press this solver flow sheet button, or just press F5 from your keyboard. Okay, now the process is already converged. Okay, so let's go and see the results. So in bottom, right click on this arrow, and from here go to the compound amounts and see the isopentane mole fraction, that is 0.01. That is okay, we specify it. Similarly, press the stop button, and from here you can see the heavy key component, that is the N-hexane, should not be more than 0.01, so that is also okay. So next, what we need from the shortcut distillation column, we need go to this result value, we need the minimum reflux ratio. So it is 0.571368. And if you recall, in problem statement, it is written the reflux ratio should be 1.5 times of minimum reflux ratio. Okay, so the minimum reflux ratio is 0.57. So in order to adjust the reflux ratio, what I am going to do, just going to multiply 1.5 into the minimum reflux ratio, that is 0.571368, and then just press enter. Okay, so this one is the actual reflux ratio that we will use. Okay, and minimum number of stages and actual number of stages, that are 14. Optimum stage location is 6.5. We will take out as a 7. And what is the molar flow rate? From the bottom side, it is 2500 and 37 kg mole per hour. if you see from here, 2537. Sorry, I have to change the molar flow because during the iteration it changed. So you just, it's better to again check either the input values are there or change. So I'm going to change this molar flow rate in the feed. Okay, and now everything seems okay. Just note down the bottom stream molar flow rate, that is 27 55 kg mole per hour, and the top one is 2244.9 kg mole per hour. Okay, so these are the results we would need as a feed for rigorous distillation column. Okay, so I'm just copying all these results here. So this is the results from the shortcut distillation column, that is the reflux ratio, actual number of stages, optimum feed stage location, and bottom product molar flow rate. Okay, so now these would be the inputs for the multi-component rigorous distillation. Okay, now what is the next step? Go to the DWSIM, right click on short column distillation and press delete, and delete this column. Okay, after deleting this column, it's time to add the rigorous distillation column, that is this one, uh, and put it into the uh, flow sheet. Okay, now go to the left side of this distillation column. I am just going to change its name, maybe the rig distillation. Okay, and go to the specification. From specification, go to the journal, and it is saying what is the how much number of stages for you want for the separation, and we already have calculated from shortcut distillation, and how many they are. So there are 14 stages for this separation, that is the result of shortcut distillation column. Just press 14, press enter, go to the next condenser, and the condenser or the top pressure is, it's given in the problem statement, that is 1.8 bar. Okay, and the condenser type is total, condenser pressure drop is 0, specification we are using reflux ratio, and we know how much is the reflux ratio is 0.857052. So 0.857, just press enter. Okay, and then go to the reboiler. So in reboiler, the first change the pressure. Reboiler will operate at 2 bar, and the bottom product molar flow rate, that is given in kg mole per hour, and from shortcut distillation column we have calculated the bottom product molar flow rate is 2755. So just press it here, 2755, and press enter. Okay, now you just specify the condenser and reboiler and the journal column specification. Now click on this configuration button, and from there go to the stream connections and feed connection. You can choose any port where you want to connect feed, but for to look better, just I am going to connect feed at the feed number 5. After that, connect product, go to the product and distillate. Just click on this and connect top as a distillate. Okay, and then from here bottom as a bottom. Okay, now go to the duties. So reboiler duty is reboiler D, and condenser duty is condenser duty. So after connecting this, now we have to assign the stream, the feed stream location. For that, just click on stream stage associations. Okay, so from shortcut column calculation, the optimum feed stage location is number 7. Okay, so click on this drop down menu and select stage number 7. Okay, now after that go to these stages and see this pressure profile that you put, because we know that the condenser operates at 1.8 pressure, 8 bar pressure, and the reboiler is at 2 bar pressure, and it is showing that at stage 11 and 12 the pressure is 0. That is incorrect. So how we can define the pressure profile inside the column? For that, go to the extreme left side of this window, and here if you click on it, it says estimate stage pressure by interpolation. Just click on it. Now it just estimated the pressure profile inside the column. Okay, so after that, again press this specification. Now we are ready to run the simulation. For that, just press solve flow sheet. Okay, now the distillation column is converged successfully. So let's go to see the results. Just click on this distillation column and then go to the results. Okay, so these are the values for condenser duty and the reboiler duty for actual separation of these multi-component separation tasks. Okay, now how you can see the temperature profile, pressure profile, flow rate profile. For that, in the result menu, just go to the bottom of this window. It says view temperature, pressure and composition profiles. Just click on it. So this one is the temperature profile. Similarly, you can have a flow profile. Similarly, you can have a separate component flow profile in both liquid phase and vapor phase. Similarly, their component fraction in both liquid phase and in vapor phase. And if you need this data in the tabular form, just from this top ribbon, click on this value table and you will have all the data in tabular form. So this is the way how you can simulate a rigorous multi-component distillation column in a very simple way in DWSIM, which is open source and free software, and it gives you a lot of liberty to modify your own custom models. So I hope you understand today's tutorial, and if you like this video, please don't forget to subscribe my channel. In coming video we will discuss about reactive distillation and what is this and how we can calculate this kind of problem statements in DWSIM. Until then, bye bye, see you next time, stay tuned.